Alright, hello guys. So, let's continue doing the IEEE floating point stuff. And of course, the next step is doing arithmetic. So I'll be doing some IEEE single floating point precision arithmetic with you guys. Arithmetic. Now let's start with doing addition and subtraction, which is kinda harder in with the IEEE because of the ones complement. So there are a few rules I want to cover with you guys first. So this is for addition and subtraction. Yes? So the first rule when doing subtraction and addition, the first rule is both the operands, so the operands being operand A and B, of course, so two numbers, they both have to have the same exponent. So it's just like with decimal calculations, with scientific notation with decimal values, they have to have the same exponent. If they don't have the same exponent, you cannot do or perform the calculation. And if they don't match, we basically always change the value with the smallest exponent. We match it to the biggest one, or to the number with the biggest exponent. Does this have an influence on the result itself? Yes and no. No, in the sense that if you would do the inverse, it could be the same result. But I say it could be the same result because it can matter when we have rounding issues. And so that's what the standard says. We always take the smallest one, convert it to the biggest one, so that we have a matching result for all of them. So always try to do match the smallest one with the biggest one. Definitely the rounding stuff, it can cause a lot of issues, so just do it. Now, the second rule here is if both the operands, their sign bits, if we take a look at it, if they match, so if both of them are, for example, negative, or both of them are positive, you can just do the operation. It's not an issue. But if they don't match, and that's the important thing, if they don't match, well, we do the opposite operation. Opposite operation. So, for example, if I would write minus A plus B, then I'll basically be doing a subtraction instead of an addition. So that's an important thing. If they don't match, you do the opposite operation. Now, the whole thing brings us to, again, the sign bit stuff, because it's all have to do with the one's complement. Rule number 3 is, well, or the third part you need to keep track of is, what is the sign bit of the result? You need to keep track of that. Now, we have a few steps here. First of all, we always match the resulting sign bit. So the results sign bit is by default the value of the first operand's sign bit. So it's the first operand's sign bit. And this is by default. So by default. If we are doing subtraction though, so if subtracting, if we are subtracting, then what we will do is we will make sure that we are always having the biggest operand, so the biggest operand of both operands, that operand is the first operand. So the biggest operand should be the first operand in the calculation. Now, if for some case the biggest operand is by default the second operand, so if the biggest operand is the second operand by default, for example, I have a minus b, and b is bigger than a, then by default the biggest operand is the second one. What I need to do then is, of course, to be able to have the biggest operand to be the first operand, I need to swap both operands. Now, of course, just like with decimal calculations, you cannot just swap two values, of course. You cannot say, whoa, 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 a minus b is not the same as b minus a. But because of the swapping, to take this into account, if we do a swap, what we do is we just invert the resulting sign bit. And remember that by default, it is equal to the sign of the first operand. So if we change or if we swap the operands, what you basically do is, so you have your sign bit of the first operand, we swap it. So if it was minus a plus b, and we do a subtraction, and b was bigger, so we have the sign bit equal to the first operand sign, which is negative. It's minus a plus b. If we need to swap them, then the resulting sign bit will be positive. We invert it. Now there's one more thing here. If for some reason both operands are equal in size, it can happen, of course, are equal. The only thing you need to know then is that when doing subtraction, the sign bit will be positive. And it's, of course, the same like in regular decimal arithmetic. If you have minus 1 plus minus a plus minus a, the result will be a positive number. So, let's start. So I know these are some rules that they can be hard to maybe remember, but if you take a look at it, or if we'll do the calculations, you'll see that it's not that hard. For the people who, of course, follow the class, you probably remember that the big graph I drew, or I have a slide of, which says if it's minus a plus b, then do this. You can't, or don't learn that column, that table out of your head. Just follow these rules. I think it's way easier to think about it and to store the process of doing everything inside your head and practice it than learning a table, which is pretty useless. It's way easier to do it this way. So don't learn the table. This was just an overview for you guys. It's a correct table, but following these rules is, in my opinion, way easier and more interesting. So let me do the first operation, which will be addition. And so let me do the following calculation. So 0.85 plus 1.25. Easy as that. And so what I basically write here is a plus b equals c. So c will be my operand, or my representation of the result. And of course, if I want to be exact here, what I basically wrote is plus a plus b. So in this case, both operands have a matching sign bit, so they are both positive. So I can just perform my addition. I don't need to do the opposite operation. So let me write down both values again. So a was 0.85, which was, if you recall, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0. And then we had b, which was 125, which was 0, 0, 1, 1, 1, 1, 1, 1, 1, and then 0, 1, 0, and all zeros. Yes. One more thing, which is what I'll be doing for the addition and subtraction. One cool thing about using one's complement is, of course, the fact that if I want to change, for example, 125 to minus 125, I'll just invert the sign bit. So if this would have been a 1, it would have been minus 1.25. So that's easy. I'll be doing that, but I'll be telling you explicitly that I did it, of course. But that's the only cool thing about using one's complement. So if I do arithmetic and I get, for example, these two values, I don't even know what the decimal representation is. The first thing I always do is I extract all the information that is important to me. So I'll start with using or extracting all the data from A. So the sign bit is 0. The exponent of A is 0, 1, 1, 1, 1, 1, 1, 0. And the mantissa of A is, I'll write down the implied bit, 1 point, and then 1, 0, 1, and then all the other values behind that. And I'll be doing the same thing for B. So sign bit is 0, the exponent of B, and the mantissa of B. And then all zeros. Don't write all the zeros in this case. Now, what is important here, if I want to do the calculations, the first rule says both of them should have the same exponent. So I have my biased exponent here. I, of course, need to unbias it to be able to do the calculation itself. So this is, of course, we know the answer here because we did the calculation ourselves. But if you just get these values, it's not that hard as well. This value represents 126, and you just subtract 127 to unbias it, and then you again get this minus 1 that we had before. And so here is the same thing. 127 minus 127 is 0. So even though you don't know or you didn't do the conversion yourself, it's pretty easy to extract the unbiased exponent again. And so once I have all this information, the first thing I do is I write down the operation with the mantissas and the exponent. So I'll write the A, which is its mantissa is with the implied bit 1.101, 1001, 1001, 1001, 1, and I write down this is with an exponent of minus 1, and I'll add b to it, so also the mantissa with the implied bit, and I'll write it beneath it so I can do the arithmetic. So 0.010, and then all zeros. With an exponent of 0. And now, of course, once you wrote it like this, you see, well, we already saw it probably, we see that both exponents don't match. And so what I'll be doing here is I'll be switching, I'll be rewriting the smallest one to match the biggest one, exponent-wise. So what I need to do to be able to represent the first number, which is an exponent of minus 1, if I want to rewrite it using an exponent of 0, I'll need to shift my radix point once to the left. So this becomes 0 point, and then 110, so 110, and then 1100, 1100, so 1100, 1100, 1100, 1100, and then 1101, 1101, and I have a remaining 0, but there are also zeros here, so I can just discard it. And so this is now an exponent of 0. And I'll keep my previous operand b as it is, of course. So I'll just take it over nothing fancy here. And now both of them are in the same, or use the same exponent. Both of them have the exact same signs, so it's an addition. So I don't even need to think about swapping operands. It's not important. This is only for subtracting. So I can just perform the binary addition here. So not that hard. So 1 plus 0 is 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0. And then we have 1 plus 1 is of course 0 with the carryover, 0 with the carryover, 0 with a carryover, which of course then drops like this. And you just take over the radix point as it is. So I have this radix point here, I'll just take over as it is. And so our result now is also with an exponent of 0. Right? So we're almost there. The only thing we need to do now is, again, if we want to store it into the IEEE format, the result should be normalized. And in this case, again, it's not normalized. It is 1, 0 point, and then all the stuff that it's behind the radix point, it should start with 1 point. So I'll just need to, again, shift my radix point, my decimal point, once to the left. And so, of course, if I do this, I get this result, 1.000, and then 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1. And because of that, my exponent switched from 0 to 1, of course. Shifted once to the left. I need to shift once to the right to represent it again. And so, of course, to be able to store it into the IEEE, I need to bias this exponent again. So it's the same thing, 1 plus 127, which becomes 128. And 128 is, of course, in binary 1, 0, 0, 0, 0, 0, 0, 0. And so, last but not least, I'll just add all the stuff together. So our sign bit is the same as the sign bit of the first one. By default, it's always like that. So it's 0. Then I'll write down my exponent, which is 1, 0, 0, 0, 0, 0, 0, 0. And then I write down everything without the implied bit. So this becomes 0, 0, 0, and then 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1. And if I take a look, if I count, it's 4, 8, 12, 16, 20, 24, 28, 32, and so my boundary is here. And I have this one over here. So what I'll do is I'll just add 3 more zeros to have a nibble. It's easier for me. And then I'll take a look, what do I need to do with this? And of course, 1, 0, 0, 0, it is equal to 8. And so this equals to the next most significant bit divided by 2. So 16 divided by 2 is also 8. And so then, we already discussed it, we need to take a look at the least significant bit of our result here. And then we see that it's a 0, which means we don't do anything. So we basically just discard this part over here. And we keep it as it is. And so, congratulations, this is the result of C. So this is our result. We have our exponent, and then we have our sign bit and its mentisa. And it's easy as that. That's the floating point addition arithmetic. So you see, it's just binary addition, with the exception, of course, with the exponent stuff. So let us do another one. Let us do subtraction, but again using same sign bit. So let me write down 0.85 minus 1.25. Or basically, again, writing down A minus B equals C, and to be exact, it's plus A minus plus B. and I'll be writing A again, the binary representation of it, which is 0, 0, 1, 1, 1, 1, 1, 1, 0, and then 1, 0, 1. Yes. And then B is 1.25, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, and then all zeros. Yes. So for subtraction, again the same thing first. Extract all the data that is important. So sign bit of A is 0. The exponent of A is 0, 1, 1, 1, 1, 1, 1, 0. The mantissa of A equals 1 point, and then 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0. Same thing for B. Sign of B equals 0. Exponent B. This, and mantissa of B is 1.010. And so again, I need to unbias it, just like with the previous example. Of course, we already know this will be -1, and this will be 0. But it's just the same thing. I just want to show you guys that. And so here again, just like with addition, I'll write them in the correct order, just using the mantissa with the implied bit and the exponent next to it. So it's A, which is 1.101, 1001, 1001, 1001, 1001, 1001, 1010 with an exponent of -1, minus 1.010 with an exponent of 0. And so here, when we do subtraction, I give you, or it's better to just write down the results of the sign bit of C here. And by default, it's the resulting, or it's by default the same value as A. So in this case, it will be 0. Yes. And so now I'll just do again the same thing. Well, I see that both exponents don't match, so what I'll be doing is I'll match the exponent of the smallest one to match the exponent of the biggest exponent. So it's the smallest exponent to the biggest exponent. So it's again the same thing as before. So this becomes 0.110, and then 1100, 1100, 1100, 1100, 1101, exponent 0, and 1.010, and all zeros. Exponent 0. Now, recall that one of the rules was, where's my paper? Remember that one of the rules was we make sure that the biggest opponent is the first opponent. If it's not the case, we swap them and we invert the sign bit. And so if we take a look at what we have here, we see that the second operand is the biggest one. It is 1.010, and then because the first operand starts as a 0. So it's easy to see that the second one is bigger. So what we need to do is we need to swap both operands, and this also implies that we need to invert the sign bit of our result. So the sign bit of our result becomes 1. And so what we have then is 1.010000000000000, exponent 0, minus 0.11011001100, exponent 0. And now I can just perform regular binary subtraction. And so I'll start with 0 minus 1, which is impossible. I need to borrow. As you see, I need to borrow completely from here. So this becomes 0. And then I'll just, like during class, write it like this, borrow it again, and keep on doing this. I know it's pretty small, but this is just binary subtraction, so shouldn't be that hard, I guess. And so 1, 0 minus 1 is 1. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. And then 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. Again, I cannot do 1 minus, 0 minus 1. So again, I need to borrow 1, 0 minus 1 is 1. 1 minus 1 is 0, and of course 0 stays 0, and I'll take over the radix point, and this number is in the same exponent, which is 0. So this is our result. And so again, I need to normalize the result, which means I need to shift my radix point twice to the right. So my result becomes 1.100, and then 1100, 1100, 1100, 1100, 11, and I can just add 2 more zeros to be consequent, because it does make a difference. Of course, because I shifted twice to the right, I need to keep this in mind, and it becomes exponent of -2. And so to be able to store it again, I need to bias this. So it's -2 plus 127, which becomes 125, which of course binary representation of 125 is 01111101. So we're almost done. We'll just combine all the stuff we just had, and again we need to take a look if we need to round the resulting mantissa in the IEEE format. And so I'll be writing sign bit, which was 1. The exponent I just calculated, well, the biased exponent, so 0111, 1101, and then the mantissa without the implied bit, so it's 100, then 1100, 1100, 1100, 1100, 1100, so it's 4, 8, 12, 16, 20, 24, 28, 20, 32. But as you can see, this is a repeating part. So I can say that we have our boundary. I can say that it will have another instance of 1100 behind this boundary. So I write this down as well. And I'll take a look at its value, which of course is 8 plus 2 is plus 4 is 12. And so 12 is bigger than 8. So remember, 16 divided by 2. This means we need to round this one up in the end result. So this becomes 1101. We add 1 to it. And so this is our result. We have our exponent, well, biased exponent, sign bit, and mantissa, which has been rounded correctly. So as you can see, the math itself, the subtraction in binary is just like with any other binary value. Of course, the steps that we need to take is a little bit different. So let us do one more addition or subtraction. So let's do an addition, but let's write it as follows. I'll write down minus 0.85 plus 1.25. And so what I'm basically writing here is A plus B equals C, but in this case it's minus A plus B. And so in this case, both sign bits of the both operands don't match, which means we need to do the opposite operation. So in our case, we will be doing a subtraction instead of an addition. And so yet again, I'll be writing down A and B. The only thing now is for A, like I mentioned, I'll be writing a 1 for its sign bit, which basically says it's minus 0.85. And then I'll take over all the other parts. So it was like this: 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0. And B is 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, and then all zeros, of course. And so, yet once more, I'll be extracting all the information that is necessary. I know it's repetitive, but it's a good habit of doing, so that you can spot all the information. Plus again, maybe you just get these values which are different each time. Yes. And then sign bit of B, 0, exponent of B, and the mantissa of B, it's 1.010, and then all zeros. So again, we already know that we need to unbias this. It's 126 minus 127, it's minus 1. We already know this, of course. This is 0. And then I'll be doing the same thing. So I know I have to do subtraction. And so I'll start by storing the sign bit of the result, which is equal to the sign bit of the first operand, which is A. And so I write down A point 101. I'll write down the mantissa again with its exponent. And then B is mantissa and its exponent. And so yet again here we see that we need to make sure that they match in both exponents. So it's again the same thing that we need to perform. So I'll need to shift my point for A once to the left. So it becomes 0.110, 1100, 1100, 1100, 1100, 1101, exponents 0. You should know the drill by now. And of course, again, it's subtraction, which says biggest operand first. Again, we see that it's the same thing here. We need to swap them. So our sign bit now becomes positive. Our resulting sign bit will be positive. And so I just rewrite them . And I hope you'll see that this will be, so doing the subtraction, I hope you see this will be the exact same thing as we did before. I need to borrow, and it will of course be exactly the same result. So I can just write down ones here. And it's a 1 here. Make sure that you don't make mistakes taking over numbers. And so it's be 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, exponent 0. And again, I need to normalize it. So I need to shift twice to the right, which becomes 1.100, then 1100, 1100, 1100, 1100, exponent minus 2, and so this repeats, of course. We need to bias this. Again, minus 2 plus 127, it's 125. 0111, 1101. And then we just, again, combine everything. So sign bit is 0 at this moment. 0, it's the exponent, biased exponent 0111, 1101, and everything without the implied bit. 100, 00, 1100, 1100, 001100. We know this repeats. We again know this is 12, which is bigger than 8, and we round up just like before. And so again we have our result. So with the exponent, the sign bit, and the mantissa. But you'll see that because of the inversion of the operation and of the swapping of the operands and storing the resulting bit, although swapped or not, or inverted or not, you'll see that the outcome is correct. So this is exactly the same number, except that this is the positive number and this is the negative number. So here we see that, of course, minus 0.85 minus 1.25 will become minus 0.4, and in this case, sorry, minus 121 minus 0.85 plus 1.25 will become positive 0.4. So you see it's both 0.4, but the one is negative, the other is positive. So you see that the magic works. All right. So we have two more arithmetic operations left, being multiplication and division. So let's start with multiplication. For this we have two extra rules, or two things that we need to take into account, and you'll see that multiplication and division is by default, rules-wise, pretty straightforward. First one being, if we do multiplication or division, the exponents don't need to match. Yay. So that's cool, right? It's easier. They don't need to match. What we need to do, though, is to know our resulting exponent, before we normalize it, of course, is we need to add both, and I'll explicitly say it, unbiased exponents. So I add both unbiased exponents. And then the other thing we need to know is, what about the sign bit? Well, the resulting sign bit is equal to XORing the sign bits of both operands. So sign bits, operands. And that's it. XORing both of them will give you the resulting sign bit. So let me again do the following calculation. So 0.85 times 1.25. So let's do this calculation. And so basically what I'm again writing here is positive A times positive B. So nothing fancy here, even though it doesn't really matter because we just XOR signs. And then let me again write A and B. So it's 0, 0, 1, 1, 1. You will probably be dreaming about these two values after this. Being chased by binary numbers. and then of course we know it repeats. And so if we do multiplication, it's pretty straightforward. I'll calculate the sign bit of the result by XORing both sign bits, so sign bit of A XOR sign bit of B, which is of course 0 XOR 0, which of course is 0. So I already know my resulting sign bit. Exponents of, or the exponent, the temporal exponent of our result is adding both unbiased exponents. So first exponent is 0, 1, 1, 1, 1, 1, 1, 0, which is of course, again, we already know it, it's -1. And we add the other one to it, which again we of course know already, which is 0. So what we do is -1 plus 0, which is -1. So hold your horses on this one. This is not the result that will be stored inside the IEEE notation. This is what we get after doing the multiplication. So before normalizing it again. You'll see it in a moment. So what you do now is you just write down both operands, as you should do for regular binary multiplication. So I'll take A, so I'll again write down the mantissa with the implied bit, so it's 1.101, then 1001, 1001, 1001, 1001, 1010, and I'll write down the second one, which is 1.01, and I'll just ignore all the other zeros, because it's pretty useless to multiply by all zeros in the end, because it won't make a difference. Alright, and so I'll just perform the regular binary addition. Multiplication. So one each at a time, and then in the end I'll add all intermediate results. And so of course 1 times 0 is 0, 1 times 1 is 1, so I can basically take over the first number completely. Then I'll be performing multiplication with the 0 for each number. Of course, take into account the fact that this is the next decimal or the next bit. So I'll shift everything once to the left. So I'll just add a point here to visualize that for myself. And I'll be writing down zeros for everything, because 0 times 1 or 0 times 0 is 0 anyway. I'll try to group them per 4. And an extra 0 because of the whole shifting stuff. And then I'll be doing the same thing for the last one, but again taking into account the fact that I shifted everything. And so this becomes 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. So I need to keep track of that. So 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1. Whew. So don't make any mistakes here. And then I'll just add all the intermediate results. So 0 plus nothing is of course 0, 1 plus nothing is 1, then it's 0. Then 1, 1 is of course 0 with a carryover. 1, 1 is a 0 with a carryover. 1, 1 with a 0 is a carryover. 1, 1 with a 0 is a carryover. 1, 1 is a 0 and a carryover. 1, 1 is a 0 carryover. 0 carryover. 0 carryover. 0 carryover. 0 and a carryover. 0 carryover. 0 carryover. So I'll just keep on carrying over ones, apparently. So 0, 0. And then here we have 1, 1, 1, which is a 1 with a carryover. 0 with a carryover, 0 with a carryover, 0 with a carryover, and a 1. Phew. And so this is by default the exponent that we calculated here. It's -1. But of course, we have this mantissa with the exponent -1, but where the hell is the radix point? Well, to be able to solve this, we just take a look at how many bits we have after the radix point in both numbers. So in this case, it's 23. So we have 23 bits behind the radix point. Here we have 2 bits behind the radix point. We just add both of them, which says we have 25 bits, and then we just calculate the amount of bits. So 4, 8, 12, 16, 20, 23, 25. And I'll just add in the point here, where we have 25 bits behind that decimal point. So this is our intermediate result. Now, of course, to be able to store it, again, we need to normalize it, which means that I need to shift my radix point once to the left, which means my result will be 1 point, then 0, 0, 0, then 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, all zeros. So it's 1, 2, 3, 4, 1, 2, 3, 4, then 0, 0, 1, 0. And of course, our exponent changes to 0 because of this. And I need to bias it again. So 0 plus 127 is 127, which is of course 0.111, so 0.1111111. And then I just write everything down, so I know my resulting sign bit, which it was 0. Start 0. My exponent 0, 1, 1, 1, 1, 1, 1, 1. And then my mantissa without the implied bit, so it's 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So it's 4, 8, 12, 16, 20, 20, 24, 28. We even have 3 more. 1, 2, 4, yes. And then we have 0, 0, 1, 0, but as we just saw, that 0, 0, 1, 0 is out of the range, so out of the memory block we have. So it's again 4, 8, 12, 16, 20, 24, 28, 32. And so I'll take a look at this. What is this value? Well, it represents 2. It is, of course, smaller than that 8, that 16 divided by 2. So we don't do anything, we just discard it. So you see that we get rid of it. So we have the solution. It's this number with this being its exponent, the sign bit, and the mantissa. So there we have it. This is the result of multiplying 0.85 times 0.25. All right, awesome. So we have one more arithmetic operation left, which is division. And here we have almost the same rules as with multiplication. So again, both operands don't need to match, or both exponents don't match both exponents. don't match don't match exponents, but instead of adding both exponents to know the intermediate exponent, we of course, instead of adding, we subtract them. So we subtract the unbiased exponents. And again, we XOR the sign bits to know the resulting sign bits. That does not change. So I mentioned a little bit earlier that I won't be doing the addition, or sorry, the division with the two numbers 0.85 and 1.25. You'll see that, or the thing that I will show you is the one from during class. It's the same thing. If you would have done it with 0.85 divided by 1.25, for example, it is exactly the same arithmetic that you need to do, but I'll show you the result. This is the longhand division that we'll need to be able to do. So you'll see that because of the fact that we have a repeating part, or a repeating number, it keeps on going. And then I even had the issue that I did not have enough bits in the mantissa to store in this 23-bit component, so I had to start doing the repeating part a few times, so I had the resulting value so I could add it to it. But it's the same thing. It's pretty, so you can do it. So you here, if you pause the video and you do it yourself, you'll see that this is correct, and that if you would do it, it's exactly the same thing. But I won't be doing it in this video. I'll take the two values from during class because both of them are finite, and it's a little bit easier to do, and it's easier to use it to explain what you need to do. But so what I'll be doing here for the division is I'll divide 7.875. I'll divide it by 2.25. So this is the operation that we'll be performing. It's A divided by B. And so A, and in this case we don't know, we didn't do the calculation ourselves. So in this case, you are given a binary representation, which is 0, 1, 0, 0, 0, 0, 0, 0, 1, and then 1, 1, 1, 1, 1, 0, 0, and all zeros. And for B, it's 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and then all zeros as well. And so yeah, I remember people during the exam or during class that had the issue of thinking that you should be able to read this value out of A just by looking at it. Again, that's not possible. You need to do the calculations to be able to read it, believe me. So here again I'll be extracting all the data. So this is a cool use case where I'll have to do it because I didn't do the conversion myself. So I'll extract the sign bit of A, which is 0, the exponent of A, which is 1, 0, 0, 0, 0, 0, 0, 1, which is of course 129. I subtract 127 out of it, and I see that my exponent is 2. And then I have my mantissa of A, which is implied bit 1, and then 1, 1, 1, 1, 1, 0, 0. And I'll be doing the same thing for B. So sign bit of B is 0 as well. The exponent of B is 1, 0, 0, 0, 0, 0, 0, 0. And then the mantissa of B is again implied bit, and then 0, 0, 1, and all zeros. Alright, so first thing, the resulting sign bit. Resulting sign bit of C is XORing, again, both sign bits. So XORing A with the sign bit of B, which is 0 XOR 0, which again is 0. Then the exponents of, or the temporary exponent of our result is subtracting both of them, so it's a, which is 2, minus, and I did not calculate it here, it's of course 128 minus 127, which is 1. So it's 2 minus 1, so our temporary exponent is 1. And then I'll be doing the division using the matrices. So I'll be dividing my number 1, so 1.1111100. I'll be dividing that with b, which is 1.001. And now the first thing that I encounter here is again that radix point. We have these two radix points. I want to get rid of that. It's not useful to have that radix point here. It makes things a little bit more complicated if you think about it. But so what we can do to get rid of it is, well, we can just shift it a few times to the right. So I can shift my radix point here to the right 3 times. And so because I did it on this part, I also need to do it here. So I need to shift it 1, 2, 3 times. And so now my radix point is here. And I'll keep it there. That's easy. And so the cool thing about this is that I now can just take over that radix point also in my result of my longhand division. And so then I'll just do binary division. So you should be able to do this. So how many times does 1001 fit into 1111? Of course, 1 times. And so I subtract that. 1 minus 1 is 0. It's 1, 1, 0. Cool. I'll drop this one. How many times does 1001 fit into 1101? Of course, 1 time. So I'll write it down again, doing the subtraction. 0, 0, 1, 0. I'll drop another 1. And of course, how many times does 1001 fit into 1001? 1 time. Doing the subtraction, we'll see that we will be having all zeros as a result, which means we found our solution. It's 1.11. So this is our solution of the mantissa division. And we're pretty lucky in this case. It happens a lot. It happens 50% of the times that we have already normalized result. It could have been 0 if it didn't fit, 0 point, and then maybe some more zeros, or a 1. And then, of course, you have to normalize it again. So always normalize your mantissa. But in this case, it's OK. And so this 1 of our, so this is an exponent of 1. Well, this is correct. So what I can do now here is I can bias that 1 again. So 1 plus 127, which is 128. Which of course is 10000000. And so in this case, the result will be our sign bit, which is 0. I write down the exponent, which is 10000000. And then I have my mantissa without the implied bit, so it's 1, 1, and then I can add all zeros to it. So 0 and then 0, 0, 0, 0, 0. Et voilà. That's our result. So exponent, sign bit, and mantissa. But so you see, this is a pretty short longhand division. Instead of doing this one and having all of this, you'll see that we don't have any repeating part even with this division. So it's a little bit harder to come by with. But it's exactly the same thing. All right. So that was the arithmetic. So it was addition, subtraction, multiplication, and division. The only thing that we have left is doing the conversion. I'll again take a short break here. I'll just pause the video and then create another small video where we're doing the or a single conversion from IEEE to decimal.